Right, so last time we were talking about double integrals, and we saw various examples, various lessons learned. Super quick, let me just go back in and talk about that. This pair of examples here has kind of a moral, which is to looking at the sort of the bad news that happened in these inside bounds versus the good news that happened in these inside bounds. The point here is that if there is a variable that's naturally viewed as an input variable, that should be put on the outside. So in particular, looking at the way that this equation here is written, x pretty naturally looks like the input variable there, not the output variable. And that's why we put that on the outside. And then as a result of that, another way to say that is that whatever's the output variable will be on the inside, and so here it is, the output variable y that we've solved for. We solved for it because it's on the inside where I have to solve for it. Right? So, I mean, it all it's two different ways of saying the same thing, but this is why that's the slicing order that gives us the more desirable iterated integral to compute. Okay. All right. Then the lesson here was try not to slice through corners. When you are slicing, if you slice through a corner, as I'm doing there, as I move in the x direction, as I am because x is on the outside, slicing through that corner, like so, is why I have to stop this integral at x equals 1 and start a new integral at x equals 1 and going forward, thus leaving me with two integrals to compute instead of one, and all else being equal, that's pretty undesirable also. So, a couple of lessons there. Think about what's a function of what, and try not to slice through corners. Okay, here's another example. Now this is, there's a bunch of kind of circumstances that will come up when you're doing double integrals, and so I'm just trying to kind of hit a representative sample of these kinds of things. So here you go one. Sometimes they don't tell you what the domain is. Sometimes the question just is phrased in such a way that doesn't get explicitly enunciated. So, for example, let's find the volume in between this surface, which we know is a paraboloid, old news, this surface, which is a plane, again, old news. We want to find the volume in between, and of course that's referring to what I have shaded here in gray, which for convenience draw over here where it'll be a little bit easier to see. There's kind of less going on, a little bit less in my way. Okay, so fine. Now it's kind of easy to argue at a quick glance that this volume, I'm going to break up this volume into a bunch of little French fries, like so, right? And the volume of a French fry, like this, is going to be the height, which is Z2 minus Z1, right? And then times the area of its little base, and the area of that little base is in fact just dA. It's the area of the corresponding piece of the, I didn't hit that right. It's the area of the corresponding piece of the domain that we've chopped up into little pieces that gave rise to the French fry in the first place. So that part's pretty straightforward. But what's the domain for this integral, right? This is a double integral. I'm eventually going to have to identify the domain as I therefore try to turn it into an iterated integral. So what's the domain? Case can be made, I think this is pretty clear, that this edge here of our domain, you can see what our domain is in the picture, at least, geometrically you can see it. Where that comes from is that's the projection of this edge, and that edge is where these two surfaces intersect. That's where this surface, namely the plane, intersects with this, colors. This surface here, namely the paraboloid. Everybody with me so far? All right, so the little detail devil is how do I identify where that intersection happens? And there is a little bit of a landmine here in the sense that a lot of students have just not really maybe seen or for whatever reason haven't thought through enough details on how to find an intersection of two surfaces. Common mistake, the big landmine that everybody steps on, a lot of students step on. Is to think, oh, well, I want to know where both of these equations are true, so I'll set these equations equal to each other. And so students will write down, for example, well, I guess I want this to equal to this. And that doesn't make any sense at all. It's an absolute non sequitur, and it sounds good and it feels good because you feel like, well, I want them to both be true. Let's set them equal. But let me just for humor value, show you another version of this wish. I want two things to be true at the same time, so I'd better set them equal to each other. If 3 is equal to 3 and 7 is equal to 7, if I want these both to be true at the same time, do I need for 3 to equal to 7? Nonsense. It's just not how it works. That's not how algebra works. It's not a thing. Does that make sense? I hope the exaggeration for emphasis is helpful there. Okay, so what I wrote down here is garbage. Right? This is not at all how you find what we need. And again, it remains that what we need is I need to know where this curve is, and so therefore I need to know where these two surfaces intersect. Okay, the way we do this is to recognize, and I'm going to zoom for visibility purposes. We know that for some points, such as this point down here, actually I wanted purple there. For this point down here, I know that the value of z from the first equation and the value of z from the second equation are different, and specifically the second one is higher and the first one is lower. Right? On the other hand, if I were to come over to, like way over here somewhere, outside of the domain I'm interested in, the green one is actually higher and the blue one is lower. Right? So I think it's a pretty easy pitch that what I'm really looking for then, the actual, the points that I need to find, let's see, I'll use orange, I guess. The points I need to find are where, such as on this curve, projection being this curve, these are the points where the green height, oh, come on, let's do that straight up. The green height and the blue height are the same. Right? I'm looking for where Z1 and Z2 are equal to each other. Does that make sense? Specifically, I emphasize, I'm looking for points x comma y, right? I'm looking for values of x and y that make the green height equal to the blue height. So, what we want to set equal to each other are not the equations. I want to set the z's equal to each other. So I want to set this z equal to that z. And of course, I'm going to have to do some work on the right-hand side. I'm going to have to actually solve for that z. Everybody with me? So it's all downhill from here, no big deal. It's really easy to solve for. Z1, of course, was already solved for. Z2 is easy to solve for. A little bit of algebra. You got to, move things around a little bit. But these are the things that need to be equal, and therefore this is the equation that I need to be true. And now it's just a matter of kind of rewriting things, and what you get down to is the equation of this circle right here. So the shadow is a circle, and here's its equation, and now you can slice it up whichever way you like by previously discussed techniques, and a bunch of details ensue. But that's the big picture strategy. Everybody happy? I'm going to point out real quick that this process of getting from there to there involves completing the square. This kind of thing does come up. I got told in retrospect, a kind of a fib when I was in, middle school, or whenever you start learning about this kind of thing, I don't remember, that completing the square is obviated by the existence of the quadratic equation. And that only makes sense if the only thing you ever do with quadratics is find roots. And this is not true, right? So in a situation like this, you really do need to know how to complete the square. So if you're shaky on completing, if you got told the same fib that I did in middle school, high school, whatever, please, brush up, make sure that you're good at completing the square. It's just unavoidably useful sometimes. Okay, and moving along. Okay, section 5, let's finish this 5.2. 5.3 is a very, very quick section. There's really only one big idea in this section. Oh, yeah, question?
Yeah, so I was just referring to the question about the listed.
Yeah.
I just want to know, sometimes when you're not given equations, which is, so nicely put, right?
Yeah.
So would you face questions like that?
Oh, sure. Yeah. No, the questions can come in various different forms because that's how reality is, right? I mean, reality comes at you in different ways sometimes, and there's any number of different ways that a surface could be. It could be described sort of verbally as it's the surface that you get when you rotate the following curve around the following axis, or it could be it's a sphere of radius blah blah centered at such and such. So, I can't give any guarantees about how the question's going to be phrased. Yeah, totally. Okay, cool. Everybody happy? All right. There's really only one big idea, and it's a very clever idea. I feel like having it be its own section of the book may be a little overstating it. So it's a nice idea, but this arguably should just be an example, maybe a sort of concluding example of the previous section. Whatever. Here we are. So the big idea is this. Sometimes when you're computing an iterated integral, you're stuck. You're totally stuck, such as in this example, or maybe you're just sort of, I hate this integral, and I wish there was another option. So, real quick, let me point out why we're stuck here. Remember, when you have an iterated integral, you start on the inside. In order to compute this, I would need to find the antiderivative of e to the x squared, and sadly, you can't. There is no closed form antiderivative of e to the x squared. It's just a weird function, and how you prove that there is no closed form antiderivative is much sophisticated. It's beyond this course, nothing to worry about. But we can't. You try as you might, you're not going to be able to get a good antiderivative there. Yes.
What does closed form mean?
It means written without using summation, summation as so. The one way you can kind of sort of compute an integral like this one is to write e to the x squared as a Taylor series, and then take an antiderivative of the Taylor series. But that's because it's a summation. It's what we call not in closed form. Yeah, great question. Okay, so I'm going to label this as undesirable. I don't want to have to deal with this, so here's the move. Just remember that when you have an iterated integral, that came from a double integral. Let's identify the underlying original double integral, even though it wasn't stated in the phrasing of the question. We know it's there. So what is it? So it's just a matter of kind of reverse engineering what you have in the given bounds. So this says y goes from 0 to 1. All right, well, there's y equals 0, there's y equals 1. That must be where my first and last slices on my domain are as I slice in the y direction. All right, next thing, I apparently have, let's see here, I'll use, orange. For any given value of y, let's see here, let me do it like this. For any given value of y, orange, the lower bound is where x is equal to y. That must have come from the curve x equals y. I mean, it says so right there. Right? Likewise, this upper bound where x is equal to 1. That must have come from the curve x equals 1. Right? So on any given y slice, x goes from this orange point, from this orange point to this purple point. And at this point, it starts to take shape, right? We can see what our domain actually looks like here. The thing that we sliced up in this way to get the iterated integral above must have been this triangle. Everybody good? So that's the big idea, is that you can reverse engineer iterated integrals back to double integrals. And once you've got it as a double integral, well, you're in business, and you can kind of do whatever you want with this double integral. Obviously, if we slice it the way we did previously, we'll have gotten right back to where we were before. So let's slice it the other way and see what happens. Notice I put my dy dx for my differentials here. And, with that slicing order decided, x bounds are from there to there. That's 0 to 1. Then for any given value of x, such as this value of x, let's see here, my starting value of y, that point, that curve, that value of y, so y equals 0 is my inner bound, my lower bound. And then let's see here, the upper bound is going to be this point, which is on that curve, which is y equals x, which I have written down somewhere else over here. So that gives me my upper bound, y equals x. Now, so what? So I've effectively turned one iterated integral into a different iterated integral. But as is often the case in math, note, same happens when you do a substitution in single variable calculus. You just turn one integral into a different integral. The hope, though, is that new different integral might be easier to evaluate. And this works out wonderfully here. This inside integral now, the place where we were just dead in the water in the other, slicing in the other order. Now this is a super easy integral, right? E to the x squared. Oh, well, x is an outside variable. That means this is all constant, and the antiderivative of a constant is constant times y. Plug in the bounds, and that purple integral just turns into x e to the x squared. At which point we get a single variable integral that is easily dealt with. Everybody happy? This is a clever move. So changing the order of integration is the way this often gets described. It is useful sometimes, such as this example. And tool for your toolbox, and we're done with section 5.3. Unless anybody has questions. What do you think? All right. Okay, so moving on to 5.4. So triple integrals. Just taking stock real quick. We came into this class aware of single variable integrals. And then after a brief flirtation with iterated integrals, we realized that the more fundamental concept is double integrals. And the motivation there was the recognition that sometimes the quantity in question is distributed one-dimensionally, or thought of as being distributed one-dimensionally, and sometimes it's distributed two-dimensionally, right? So I can talk about the mass of a rod or the mass of a chain, something like that, and we think of that as mass per unit length. By the way, let me recognize that when chain is not actually one-dimensional, right? But when you go to the hardware store and you say, hey, I'm interested in this chain over here, how much does that chain weigh? They're not going to tell you the mass of the entire spool. They're not going to tell you the density of the metal itself, right? The way people use chain is in a linear sense, and so they will tell you the mass of, let's say 1 foot or 1 yard or whatever, depending on where you are, maybe a meter, of that chain, right? And so even though it's not actually one-dimensional, we think of it as effectively one-dimensional. Okay, well, sometimes things are distributed one-dimensionally, sometimes two-dimensionally, sometimes three-dimensionally. It's, right, a perfectly natural extension of these ideas. And in fact, if you think about it, it's arguably the more natural way to think of mass being distributed, right? That's how we grew up. When I was in middle school, they told me the definition of density was mass per unit volume. That was a very narrow point of view, of course. We're broadening that point of view, but the point is, this is the one we all heard first. So this is not really that creepy of an idea. And if you find yourself looking at a question like this, where we have mass distributed over a 3D region, and I want to know the total amount of mass, or I know the density locally as a function, what I need to do is do a Riemann sum, chop it up, add it up, whole the sum of the parts, on a three-dimensional solid instead of a two-dimensional region or a one-dimensional interval. So we're going to do the same thing we've done before, morally. I mean, different details. We're going to take this whole, we're going to chop it up into a bunch of little pieces. Here's the whole box, right, over which, let's say, mass is distributed. I'm going to chop it up into little sub-boxes, on which it's really easy to talk about mass. Mass is density times volume. Of course it is. Old news. Tiny little piece like that. The density is approximately constant. We're going to eventually take a limit to make round-off errors go away. So simple story on the pieces, and then I'm just going to add up over all of those pieces. And we've got to write that down and some details to work out, but that's the big strategy. Of course, in order to make sense out of what we're about to write down there, I do need to know how to chop up an interval on the x-axis. Been there. Just like with double integrals and single integrals. Ditto, I need to know how to chop up an interval on the y-axis. Been there. It's exact same as it is for double integrals. And so the only bit of news is how do we slice up an interval on the z-axis, and no, we have not been there, but again, it's the same kind of thing. I mean, we're still taking two endpoints, their difference divides by n, and then we incrementally add that increment, as we move on up the pieces. So, morally the same idea, total ripoff of those old ideas. And that gives us the necessary additional details. And here's the definition. This is a definition of a. Let me first just write it down. This is chop it up, add it up over that three-dimensional solid. On each little piece, we're multiplying quantity per unit volume times volume. Yeah. Whatever the quantity is. Doesn't have to be mass. It could be any quantity. We'll figure out our integrand later, right? But quantity per unit volume times volume is an easy question when you know quantity per unit volume. But then we add up over the whole, again with the colors. We add up over the whole region, take a limit, make the round-off errors go away. This is morally the same idea as a single-index Riemann sum or a two-index Riemann sum. Same idea, just three-dimensional. That's all it is. Is everybody happy with that? And it's easy to look at this expression, get overwhelmed by the subscripts and the superscripts and there's three different indices, and somebody said infinity. That's scary. But all that's happening here is we're chopping something up into little pieces and then adding up those pieces. And in practice, we're never going to deal with all those scary-looking details anyway. So the big takeaway on this three-index Riemann sum is that it's a strategy of chopping a complicated large problem into easy small problems and then adding it. All right. So that said, turns out this applies to a tremendous number of examples. No surprise. Right? So this is worthy of a name and a notation. The name is triple integral. This is what a triple integral is. It's a Riemann sum. In practice, we don't write it like that because it's bulky and clunky. So we write it like this instead. This is our shorthand notation. And again, this is just shorthand for saying we're looking at little pieces of volume. And this over here is shorthand for saying we're going to then add up the answers to those easy questions over all n cubed sub boxes and take a limit as n goes to infinity. So it's just notation, nice little convenient, compact notational shorthand. Triple integrals fundamentally, intrinsically are Riemann sums. How are we doing? Is everybody happy? Okay. All right. And again, the book is more mathy and rigorous and proofy than our course aims for. So all this business about irregular partitions and arbitrary test points. If you're curious to glance at it for curiosity, you're welcome, but you're not obligated. It's not part of the course. All right. So now this first example is this is the motivating example, so it's almost repetitious. But let's just make a put a final nail in this as a concept. If you find yourself needing to compute a mass where density is given, density specifically is mass per unit volume, then the total mass is the sum of the masses in the sub-boxes. The whole is the sum of the parts. That's this first thing. Again, notice I'm using this convenient integral shorthand. What this actually is a Riemann sum, but it's just easy to write it like that, right? And then on each little piece, mass is density times volume. And we find ourselves then with a triple integral, and so the remaining question is how do I compute triple integrals, which, that's going to be a whole nother thing, but we've successfully written the answer to this example as a triple integral. What do you think? All right. Okay. So I want to warn y'all about one thing. Y'all heard me give this speech about how, I'm a little bit cool on the idea of thinking of single variable integrals as being area under a curve. It's not that it isn't area under a curve. Yeah, this is it's certainly one of the most commonly discussed examples. It is geometrically satisfying. A lot of good things you can say about the area under a curve metaphor for single variable integrals. I like it in that sense. I do think it's overappreciated. It's to the point that it's kind of a crutch, and students think that fundamentally what an integral is area under a curve, and that is not true. That is not fundamentally what an integral is. That's one not even all that intrinsically useful example, right? It's only sort of for intuitive purpose. But very rarely do I need to know the area under an actual physical curve, right? Okay. And I tend to push instead this other point of view of, I don't know, I find this intuitively also satisfying in a different way. Mass of a one-dimensional distribution, let's think of it, for example, as a metal rod with non-constant density. So what I like about this metaphor is that it is pretty relatable, maybe not quite as much as area, but it's also not sort of, it's not something that we're going to get dependent on. It's quantity per unit size, which I'm viewing as it is, as a size, right? And so it's a little bit more sort of honest in a way. So again, I've been pushing, don't rely on the area point of view, start thinking more in terms of the mass point of view. And then the same deal here when you're doing double integrals. And again, this is somewhat okay, I suppose. It's got its merits to think of double integrals as computing volume under a surface. And it does compute volume under a surface. And that's even a little bit more routinely actually useful. The real world really is full of volumes that we'd like to be able to compute. That's true. But still, it's not really what we most of the time need. Most of the time, when you're computing a double integral, you're interested in something else. It's usually not volume. So, again, it's a nice crutch. Again, it's overused. Again, I'm trying to pull students kind of away from that and toward, instead, this kind of an example here. Which I feel like, again, has a little bit more sort of geometrically representative of the idea of we have a two-dimensional domain. Look at this, I'm looking at a two-dimensional domain. Quantity is distributed across that two-dimensional domain. Again, that's how I've got the picture drawn. So I feel like this is a little bit more, I'm going to say honest, for lack of a better word. Okay, but here's another reason now of why I, just broadly speaking, tend to be cool on this point of view and happy about this point of view, and that is what happens if we extend the analogy to triple integrals. Right, and just keep track of the numbers here. Over here on the blue side of things, single one-dimensional integral has a two-dimensional picture here. Right, I'll do it like this. One-dimensional integral has a two-dimensional picture. Two-dimensional integral here has a three-dimensional picture. What would the three-dimensional integral, triple integral picture look like? Well, it's a four-dimensional picture. And we lose. Right? That's you can't visualize four-dimensionally. I mean, you can kind of fool yourself into thinking you can, and you can even kind of draw some conclusions by thinking by analogies, and there's some techniques that are useful there, and anyone who's curious can come talk to me in office hours. It's kind of fun. But you certainly can't draw four-dimensionally, right? So at best, this is a very, very unsatisfying point of view. Whereas if you look at the dimensions happening over here in the mass metaphor, one-dimensional integral, one-dimensional picture. Two-dimensional integral, two-dimensional picture. Triple integral, three-dimensional picture. No problem. In business. Fine. Everybody see the problem? So, anyway, look, be aware, all of this is fine. You are welcome to, and you should understand these points of view, yes. The problem that comes up is that some students will insist on thinking of single variable integrals this way, insist on thinking of double integrals this way, and then be forced into thinking of triple integrals this way, and then never really quite sort out in their minds why this three-dimensional picture and this three-dimensional picture are different. Whoops, I got the smile going the wrong way. So how come sometimes a three-dimensional picture is a triple integral, sometimes it's a double integral? What gives? And never really get any satisfaction out of that question, right? So, in order to make the best sense out of this picture that we have to think of for triple integrals, right? To get the most satisfaction out of that, you have to first get comfortable with thinking of the easier, earlier, lower dimensional integrals in the analogous way. So, anyway, that's the purpose of this little soapbox speech. I hope that helps. Beware of the dangers there. Okay. All right. Good news. Triple integrals can be computed with iterated integrals. Thankfully. Now, I'm not going to be able to make much of a case for you on this as to why this is true, because after all, the way we did the equivalent statement here for double integrals was I drew a three-dimensional picture. Right? We had a two-dimensional double integral, two-dimensional iterated integrals. We drew the three-dimensional picture of volume. We argued we can compute it either way, and therefore these things must be equal. If I were to do something analogous here, it'd be a four-dimensional picture out of the question. Right? It's a non-starter. So I'm not going to be able to make the case. There is, however, there are other points of view on how you can connect these things. Algebraic points of view that are very rigorous and somewhat satisfying, I suppose, but there's heavy machinery and things to worry about. And I am just going to, for the purposes of Math 219, just ask you to believe that this should work out analogously as we would expect. And I think this is a pretty easy pitch. So, good news. Triple integrals computed with iterated integrals. And here we are again with our three-step process. This is the analogous picture that we drew for double integrals. And we can connect applications directly to Riemann sums. Mass is mass per unit volume times volume. Chop it up, add it up, right? Or so easy examples that we can easy arguments that we can make in these situations. And knowing, as we do now, if you believe me, that triple integrals can be computed with iterated integrals, all it comes down to then is how do I compute iterated integrals? And I think this is another pretty easy pitch. Iterated integrals are single variable integrals. We already know how to compute them. It's single variable integral of a single variable integral of a single variable integral. So, plug and chug. Right? So, again, there's our roadmap. Again, heads up, please don't try to think of this in a four-dimensional way that's a formula for disaster. You're never going to really get satisfaction of thinking of mass as being a four-dimensional geometric object. It doesn't really make sense. Even if you could visualize in 4 dimensions, the case for claiming these are the same just doesn't make sense. Without it, other than being unless you argue by way of Riemann sums, which again, what's the point? And furthermore, please don't make the mistake of thinking that you can just bypass triple integrals entirely and just directly argue that mass is an iterated integral. Again, you get this problem with the units mismatch. You'd find yourself writing down and trying to make sense out of mass per unit volume times length. What is that? That's not a pre-existing natural idea. Even if you could make sense out of it, it would be narrowly applied to that one specific application. You'd have to, it's extremely inefficient and impractical. So that doesn't work either. So again, we need a 3-step process. Again, please make sure you show me all 3 steps. I need to see the triple integral. I then need to see that you've rewritten the triple integral as an iterated integral, and then plug and chug with the fundamental theorem. Let's dive in and see an example. Suppose I want to compute the amount of mass in this rectangular box. Again, note the notation. X range, Y range, Z range. Where mass per unit volume is given by this formula here. And the first step, phase 1, chop it up, add it up. Little pieces of mass are density times little pieces of volume. Okay. How we doing? Is everybody all right with that? Okay. Phase 2, triple integrals are iterated integrals. Right? And of course now the bounds there, in this case we can read straight off this saying that the range of values of x is from 1 to 2. Okay, well then the x bounds 1 to 2. And likewise the y bounds 0 to 2. Likewise the z bounds 0 to 1. Right? And then phase 3, plug and chug, and go for it. It's just like with double integrals, just a little bit more so. There's 3 of them instead of 2 of them. Again, one of the big things to watch out for is, well, there's two things to watch out for. The exact same 2 things to watch out for as with double integrals. First, don't forget that as you're doing, let's say the inside integral, where of course you have to start, the variables further to the outside are constants. So x and y are constants for the purposes of the inside dz integral. Well, that means x and y there in that integrand, constants, or we're going to treat them as constants as they are for this integral. And so they do what constants do. They just kind of follow down here. Right? And as far as the actual computation of the integral goes, z is our variable. And so we're doing an integral of 2z with respect to z. Well, no problem. That's z squared. Constants come along for the ride. Everybody good? So again, now this is, the responsibility of the person working out the integral to keep track of what variables are playing what roles for which integrals as you go along. And again, the rule, variables further to the outside are constants. Okay. All right, second little landmine issue to keep track of, just like with single variable, just don't forget that these numbers are values of that variable, and I think it's a healthy exercise to explicitly note that as you recopy the bounds about to plug in. Otherwise, if you don't, if you were to kind of leave that off and leave that off and just put 0 and 1, it'd be easy to not only plug in that value for z as it should, but to perhaps inadvertently, accidentally also plug it in for all the other variables, which of course is just wrong, very wrong. Easy mistake to make if there's no visual reminder. And notice in what's written down here, nowhere in that box does it currently indicate which variable the 0 and the 1 are supposed to be plugged in for. So you're leaving yourself in a precarious situation if you don't do this. So again, all you got to do, it'll take you 3/4 of a second, right? Is just write z equals 0 and z equals 1. Nothing to it. Again, not required. It's just advice. Hope it might help. Okay. So triple integral turns into then a double integral, and double integral turns into a single integral, which then you can compute. So 3-step process, just like double integrals. Alrighty, moving along. Well, what's the deal with non-rectangular domains? Well, again, I can't make the geometric argument, because the geometric argument that I made when we faced this point with double integrals was the 3-dimensional picture. So if I was going to do something analogous here, it'd be a 4-dimensional picture, and I can't do it. So I can't make that geometric case. What I'm going to do is again just assert, ask you to trust me that it's an analogous process. And I think this is a highly believable. But I want to emphasize I'm not going to prove what I'm about to say. I'm just going to assert it, and I think this is the appropriate choice for Math 219. But anyway, so that process that you'll recall from double integrals is that we always start off. Let's see here. In which order am I? It looks like I'm doing x. Yeah, okay, all right. So we start off having chosen a direction in which to do our slicing at first. And of course, slices in the x direction, what that means is we slice by constant values of that variable, and an x slice then would be something like this, right? That's what our x slices of this random arbitrary solid look like. So we slice orthogonal to our outside variable axis. Next, we identify the bounds by looking at the first slice and the last slice in that slicing process, right? So x1 comes from that point, x2 comes from that point, and once those are found, you then fix a slice. So we're going to fix x to be there. Our x slice looks like this. And we move on to the next axis, to the next variable. And let's see here, the way I have this written here, we have our orange x slicing on the outside, and moving inward, we now get to y. And so I'm going to be slicing next in the y direction. And the process repeats, right? So specifically, we're going to slice perpendicular to the coordinate axis. Now, again, think through, what does it look like when I take a slice perpendicular to the y-axis? Slices are vertical planes like that. We have now a little bit of a geometry challenge. What happens when I take my existing x slice and slice it perpendicular to the y-axis. Geometric appeal, that slice is sort of a line segment. Like that. Right? We've got to look at first and last. The first y slice, the first y slice is going to be, over there. The last one is going to be that point, and that's going to tell you your y bounds, which, you're going to have to use the geometry of the situation. We're going to do a bazillion examples, by the way. So I'm just kind of trying to outline the process here. We'll have to, do the appropriate work to find those y bounds. And once you've done that, then, again, as usual, we need to fix now a y slice. Now, my picture's getting muddied, so I'm going to sort of start this picture over. Having already fixed x, and now further having fixed y, our y slice looks just like that, and only that. And now I have to proceed again. Right? Third step through this process. Again, just the same process we did for double integrals, just kind of three-dimensionally. Now we have to look and see what is our third slicing direction, z. So I've got to take this y slice of my x slice. I need to slice it orthogonal now to the z-axis. Slices orthogonal to the z-axis look like this. Again, a geometric appeal, if I take this blue vertical line segment and if I slice it now horizontally, well, I just get points. Like that. And where's the first, where's the last? Well, the first one is clearly there. The last one is clearly there. And those will be my inside bounds. And that tells me all my bounds. And that gives me a triple iterated integral that I can just compute. Everybody with me? Let's do one. Oh, you know what? Before we dive in, a couple of observations I want to make. This is just reminders. Terminology. Tempting to call these first, second, and third. In fact, I think I even did so as I was talking through this slicing process, because as you slice, this is where your first slice is, this is the second slice, and this is the third slice through the slicing process. However, when it comes to computation, right? Computationally, we're going to be doing that one first, this one second, and this one third. So again, this terminology is a problem. It's intrinsically confusing. So I like to use inside and outside, just like for double integrals, the obvious way. And then this other one here, in fact, you can call it second, because it's second, whichever order you're going in. That's a lucky break, right? So you can call it the second one. I also sometimes call it the middle one. But anyway, again, just be aware of the terminology danger and be clear. Okay, next thing. As you're doing the inside integral, don't forget variables further to the outside, x and y here. Variables further to the outside are constant. For the purposes of doing that dz integral, treat x and y as constants because they are. Again, you can see that right here in the picture. We don't get to that z integral until after we have already set x and y as fixed. Okay. All right. Likewise then, once having done that, when you're doing this middle integral, second integral, take your pick, when you're doing that, there won't be any z's left. The z's have integrated out. You'll have just y's and x's, and don't forget that x, being further to the outside, means x is constant for the purposes of that second blue integral here. So make sure to be careful about that, and I think I have these points noted. Yeah, right. So, and then lastly, same strategy for how to find the bounds. We're going to look at the key points. We'll recognize those points as being on certain surfaces. Those surfaces have certain equations that we will write down, and we'll proceed from there. Okay, so let's get one under our belts here. Here is a tetrahedron. Let's suppose we have mass distributed across this tetrahedron. Solid tetrahedron, that is. How would I, having written a triple integral to represent the answer to my question, whatever that question is, how do I turn this triple integral into an iterated integral? And it's just a matter of identifying the relevant points. Arbitrarily, I'm doing my x slicing first. X starts with that first x slice being back there. Here's my arbitrary x slice somewhere in the middle. Here's my last x slice there. And I think a pretty easy pitch can be made that x is equal to 0 on the first slice and x is equal to 1 on the last slice. It's a matter of looking at the geometry of the picture. Everybody buy it? Okay. Now, per the usual instructions, we have to fix a value of that variable. I'm going to switch to green so that my picture doesn't get ugly. There's an arbitrary fixed value of x. And now we have to do, apparently, y slicing. And y slices look like this. There's the first one. There's the last one. The first one is pretty clearly where y is 0. Here's where you have to start thinking carefully. Let's think now about where this last one is. What can I say about this point right there? That's the point. That's the key point that's going to help us find this upper bound. And again, trust the process. That point is on various surfaces. Let's identify those surfaces. It's on, for example, that surface that has that equation. It is also on this surface that has that equation. And don't forget, x has been fixed and may be treated as known because we've already done the x slicing. So with all of this in mind, and with the understanding that my answer may be a function of x, and probably will be a function of x, I just have to solve for what I'm interested in. I got to solve for y. There it is. There's the lone y, so it's easy to solve for. And there's the formula you get. Everybody see the process there? The algebra is not the point here. The point is, where did the algebra come from? What is the process that led to the algebra? And thus, upper bound 1 minus x. And I'm out of time. I'm sorry. So we'll pick up here on Wednesday. Hope you all have a good rest of your Monday. Have a good one. See you later.